Thank you. Um, Thank you for allowing me to do this virtual. It was uh, really a great blessing for that. So very appreciated. I hope that audio and video will be fine in the presenting. So my name is Chris van Hees. I work in the Linux engineering department at Oracle, specifically dealing with tracing tools at this point. I've been involved with GCC work and similar things, but let's say for the majority of, more than think about 10, 15 years by now, it's been definitely on tracing. And so I'm going to talk a little bit about DTrace specifically. So I'll give a very short overview of DTrace on Linux, and then, very briefly say what we mean with programmable dynamic tracing, and then delve into actually the bulk, which is for one, the joy of it being a product, which means we have some limitations we have to deal with, and then various other challenges we've run into in implementing DTrace and still deal with. And then I'll highlight a couple of features that we need at the kernel level that are being worked on in terms of being submitted for upstream. So DTrace. So DTrace for Linux started in 2010. And I originally had said I did not believe DTrace was feasible on Linux, and then was asked to implement it anyway. So that is where the whole thing started. So that was a version that used some code in the kernel itself. It was fairly invasive changes that were necessary at the kernel level, and then a bunch of kernel modules that work with that, and then there was user space components. So between 2018 and 2020, we started transitioning to a version that would be based on kernel facilities, including eBPF, primarily because they had matured quite a bit. So the need for the invasive changes wasn't really there as much anymore. And also to make DTrace actually something that would be eventually possible to be implemented for any kernel, for any upstream kernel, not needing these specific patches, which we had to face it, were never something that was going to be accepted in an upstream kernel. So DTrace provides tracing both for kernel space and user space. Obviously all tracing is done at the kernel level, but it's done in a consistent manner so you can truly see through the whole stack what is going on in your system. It uses a C-style kind of scripting language, is what I would call it, which gets compiled into BPF. We have various higher-level data structures that have been implemented, and so you associate actions with probes, and then there is speculative tracing that makes it possible to commit or drop tracing data that was collected based on later events. So with programmable dynamic tracing, we're really looking at code written in classes, code that is going to be associated with probes and essentially acts like functions. Whenever the probe fires, this code that we specified is going to run, and we can add conditional clauses through predicates, and you can really combine everything. You can have any number of classes that are associated with probe fires. Multiple things can be executed, obviously in an orderly fashion, one after the other. And you can have any number of probes that could be associated with this code, because you might have some tracing data you want to collect for a whole series of probes, so you can write that as one single class or function. And if any of those probe fires, that will be executed. And it should be dynamic. It should be, you can start DTrace and just give it a script. You can do it as a command line, but it's something that gets compiled dynamically and loaded straight into the kernel. So this is a little bit of an example of a DScript. It's not complete, but it should highlight sufficiently what I want to focus on. And it combines multiple probe types, which is kind of the main point here. So we have function boundary tracing probes. They're literally probes for a kernel function, either at entry or at return, similar to k-probing, k-return probe. That is the underlying mechanism for these. We're also using in this script a specific trace point in the kernel. Then we have the system call provider, which lets us trace system calls, which again is using system call trace points at the kernel level. And then we have this proc provider, which is a form of probes that DTrace provides. It's a documented set of probes for statically defined tracing that users should be able to count on that they exist. Now, obviously, they do not exist like that specifically in the kernel. So we use some other underlying probe to provide this. In this case, we're actually using the trace point of the probe above it, the get process exits. And when that trace point in the kernel is reached, it will actually also have to execute the code for this proc provider trace points. And I'll get into that a little bit and how that gets done. But as you can see, you can have a mix of different kind of probes in your particular script, and you might have multiple probes attached to a particular fragment of code, and that all makes for some interesting complexities. So each of these clauses, each of these code blocks are compiled into a BPF function. At this point, we're looking at it from that perspective. It's just code generated as a function. We're not doing anything with it yet. And then DTrace probes are mapped to kernel level probes. So whatever happens in DTrace, what you see may be different underneath the covers, but that's not something that users should have to worry about. So we have the FBT probes, as I mentioned, system call probes, the profile probes for timer events. There's user space probes that you can do using uprobes. And then these special statically defined tracing probes that are mapped to other probes. And sometimes it's a combination of probes. So there's a couple of cases where, because of limitation on how to get to data and the specifically documented point at which a probe should fire, that we have to have one probe first, which stores some data away in a BPF map. And then when a secondary probe fires, that is the one that is actually going to trigger the reporting of this SDT probe having fired and then is able to attach the data to that. So that's a technique we found to be working fairly well, and it has taught us a whole lot about working with BPF. And then we also have some common subroutines that are implemented using pre-compiled BPF code using the BPF support in GCC and binutils that Jose's team has contributed. And that has been a really big benefit for us because it's code that is not dynamic. It's pre-written code for common subroutines. It might be as basic as doing a substring, looking for a character in a string. We have subroutines for converting IPv4 and IPv6 addresses into their string representation. So this kind of code really lends itself well to be pre-compiled. So obviously with BPF and probing, a program is being attached to a kernel level probe. So we have to play with that a little bit because in BPF, as you probably know, there is different program types. Specific kind of probes have specific program types and they have their own context associated with them. And that becomes a problem for us because in DTrace, there is a very strong concept of a generic probe. All probes are essentially the same thing. There might be differences in naming, obviously, but the probe argument is where things really show. But the way a probe acts is exactly the same. So a piece of code is being generated based on this generic probe concept. And so we had to kind of figure out a way to make this possible where we could have code that is essentially compiled literally once, but can be associated with different probes to therefore be part of different program types. And that creates some complexities. So what we have done is that the BPF program that is being associated with the probes is essentially generated as a trampoline. So first of all, we have this global on-off switch built in, which is very important for DTrace. We need to be able to attach all the BPF programs to the probes we need. And then there needs to be a specific point in time where we can say probing starts now. So we don't collect any data before that point. And it cannot be done in the consumer because that is obviously running asynchronous from the actual probing. So the first thing is a check whether tracing is on. If not, we basically immediately exit the program. And then we set up this DTrace context, which is really building a context that describes this probe in a genetic context in a way that DTrace can work with. And that makes it possible that no matter which program type we're operating in, all further code after this point is going to operate on this DTrace context. It keeps the BPF context as well because we need it for things like writing to the perf buffer. But as far as DTrace code is concerned, the code we dynamically generate and the precompiled code, the probe is represented by this DTrace context. And then we do basic setup to make it possible to run our programs, and then we just call in sequence all the classes. And obviously we have to check to see if our tracing is still on or not. And then there is this special case we added recently where if there are dependent probes, these SDT probes that are implemented on another underlying probe, if those exist, then we essentially have to change this DTrace context to represent this dependent probe, like in the case with the proc provider, that proc probe. So we rewrite the context, then call the classes that are in my script for that particular probe, and then restore the context back to its original state, because there might be multiple dependent probes and they all are implemented based on the assumption that they're kind of the only one. So that's how that all works out. So then we have this final BPF program, which is essentially constructed by running this trampoline through a custom linker, or linker stage, I should say, which is just recursively going to resolve all the references. And so that pulls in the dynamically generated code and the precompiled code to create a program that is, all contained, as would be expected. And then we patch various offsets for functions, and we also resolve symbolic references because there are certain constants we need that are compilation specific and won't be known until all the other code is compiled. So it's a fairly standard way of working for this. But it was an interesting challenge to bring all these pieces together in a way that was very consistent. So it sounds easy. And yes, it was too easy. The first time was really good, and then we started finding all the downfalls. So one of the big challenges we have with DTrace, and it's just the nature of the beast. It's a product. So we have to keep supporting it. And so currently we are supporting it on 5.4 based kernels and 5.15 based kernels, while we're doing our development on newer kernels, usually try to get the most recent kernels. And that obviously, you can imagine has quite some consequences. So one big problem has been kernel helpers. It's been really wonderful to see the amount of BPF helpers grow, through the history of kernel releases. But it's also the downfall that we get very excited that we now have a helper that can accomplish something we need, and then realizing that we still have an older kernel we need to also support, which does not have this helper. So we have to work with that. There is also the BPF verifier, which has again been getting much more advanced, but that also has the issue that we can't necessarily count on its behavior as well as we would have hoped. And then there are some changes that happen in kernel source that make it something we have to adapt to, and that actually has not happened very much, which has been very surprising, but I'm very grateful for that. And again, we need to retain documented behavior. DTrace is defined in a certain way on what it is as a product, and we have less flexibility in changing that. So in terms of the BPF helpers, and I'm just calling out two cases, but there's been a couple of others, but it's an example. So BPF probe read and probe read string seemed to be a great thing for us very early on. I was very excited that we could use them for kernel and user space addresses, and then found that doesn't work on all architectures. And it kind of used to work mainly because you, in a sense, got lucky on this, how memory is mapped and how segmentation works. And so newer helpers were introduced to specifically read from kernel space versus user space. And we found that as a combination of them being introduced and also dealing with kernels being produced by Oracle, where we had some backports of various features, we ended up with some kernel versions where it was very confusing to know what worked and what did not, which kernel helper you are supposed to use for this. And so we had to introduce a mechanism to make it possible to adapt to that, especially because DTrace, again, as a product, is compiled on a specific system, but we don't know necessarily what kernel it will be used with at runtime. So we built in some logic to deal with that. And then the case for being able to get to task registers, because not all probes give you access to the set of registers in the BPF context. Again, great that there were helpers and that there are helpers now that make that possible for us, but we had to then implement a not so clean way of basically doing the same thing without using the helper. So we've always been hoping that with helpers we've been able to avoid having to write the code ourselves, but as long as we have to support older kernels, we really can't get away from that. And then the BPF verifier. It's a beautiful thing. I think it's kind of, from my perspective, it's a bit of a love-hate relationship with the verifier. It guarantees safety for programs. But that means that there are safe programs that may not make it through the verifier because it can't always guarantee that it can prove that the program is safe. And since we're generating programs dynamically, that means that we have a challenge. We have to make sure that the programs we generate will not be rejected by the verifier. So it limits us not to just generating correct codes, but also verifiable code. And that definitely has been a very interesting problem. Given the fact that we are dealing with different verifier implementations, and we need to pass them all, DTrace needs to work on all the supported kernels. We've really had to do an approach of trial and error. We've had to make DTrace generate programs that perfectly pass the verifier on our development system, and then we test it on our production test systems and find that older verifiers are not able to handle this. And so we had to come up with creative solutions that can satisfy all the verifiers we're dealing with. Fortunately, we have not seen too many issues where there's a real disconnect between, let's say, two different kernel versions where it would pass on one and not on the other, and then you fix it and then it suddenly fails on the other one. But it definitely has been an interesting case of trying to understand how the verifier works and try to somewhat predict what the behavior is going to be. So since it uses static evaluation in the verifier for instruction sequences, there's a limit. You can't hold the verifier busy for too long. So there's 1 million instructions because this is, privileged programs, and that seemed to be a really good limit until we started working with it, and now it seems very, very low. One of the problems is that it has limited state saving capabilities. It's a compiler can spend a whole lot of time generating code that it knows it's safe because it has been able to like do a full analysis using very complex reasoning, but the verifier can basically not replicate it because it's looking at the end product. And so there are cases where the compiler can guarantee that the program is correct. The verifier has no way of knowing because it doesn't know the relation between, for instance, certain data items. That's especially a problem with loops, because once you hit the case where the verifier is not able to ascertain that there is a specific invariant in this loop, and other than that, the loop is safe, it has to evaluate this loop for every possible input value. And that has taught us very well to put range limitation statements into our code to make sure that we give hints to the verifier. And another issue that we found was with function calls, that if there is a return value, that the verifier sometimes may have to evaluate all further code based on any possible return value. Again, it's a value range issue there. So we started adding in essentially pointless branches, branches that will never amount to anything, but they give the verifier a hint about the value range. So we're essentially just telling the verifier that, for instance, just jump to the exit label of our program if a certain value is out of range, and we just know the value will never be out of range, but the verifier doesn't know it, and this will help it have this information. That brought up the challenge that sometimes we ended up with creating that code because we added some extra code in there that then turned out would never be executed, and the verifier did not like that. So there's definitely another challenge there. The implementation of the verifier is very complex. I mean, it's a great piece of work. It makes it very hard to understand, especially if you're looking at different versions. So looking at your BPF code and trying to predict how the BPF verifier is going to deal with it, yeah, it can be very difficult. I have a lot of times I've written code that I was fairly certain it would accept, and it got rejected. And then quite often it did point out that, there was some issues with my code. And there were other times where I thought, okay, this will never pass, and it was able to verify that it's actually safe. So that was definitely an interesting thing to work with. And then the problem is also that sometimes when there is a failure, it can be tricky to figure out why, especially because with generated code, it's sometimes a little bit more bulky. It takes some analysis, and that's part of the challenge here. Now, another issue we have run into, and this is not related to BPF, the bulk here was, is that we have use cases with very, very large amount of probes. And we found recently that creating a very large amount of K probes or U probes is slow, and removing them is also very slow. One recent case I looked at, we had about 51,000 probes to clean up, which almost took a full minute. And that's kind of not acceptable for what we're dealing with. So far, we've been able to locate that the problem seems to be in the management of data structure at the kernel level, and it's something that we want to look more at and definitely are seeking some help with. We had similar issues with the previous version of DTrace, the one that was used to more invasive implementation. And at that time, we basically bypassed the problem by implementing our own way of doing function boundary tracing, but we don't have that option here. So that is an area where we definitely are looking at and are going to need more help with from people more involved with the implementation of K probes and U probes to see what can be done there. And maybe we're doing something wrong. But from anything we've seen so far, there definitely seems to be an issue there. Just highlighting 3 features that we do depend on that are not currently in the upstream kernel. In order to be able to provide stable naming for probes, which is based on a provider module function and name concept, the expectation is that probes that belong to a certain kernel module, whether a module is compiled into the kernel or whether it's done as a loadable module, the name should be the same. So we should be able to associate the module name with, for instance, with function boundary tracing with the function that we're tracing. And that is currently not available. And Nick Alcock has submitted a patch for that for a KL mod sims or whatever similarly named thing it might be that associates module names with symbols in the kernel. We're also making use of data type information, which traditionally has been done through CTF, which is also supported in GCC and being utilized at this point. And so that is another work that is to be submitted for upstream consideration for the kernel to be able to generate CTF data for the kernel, which then can be used by DTrace. And then finally, there's a little component where we found that being able to use a poll interface to both look for data that is being collected and state changes of process and things like that, that the existing mechanism in the kernel is not adequate for that. And so another patch that is to be submitted for the upstream kernel implements waitfd that would make this possible for us. So that's kind of an overview of what we've been working on and the challenges we've been looking into. So at this point, would point you to our GitHub repository, especially the dev branch there where all our work is ongoing and can be observed. And then definitely our mailing list for anybody who has questions, wants to get involved, anything like that. So at this point, I'll open it up to questions.
Thank you, Chris. Questions?
Hey, I have more of a usage question because I haven't used DTrace yet, but I see a pretty big overlap with BPF trace, and I've also heard BPF trace when it was first released. It was described as DTrace 2.0. So I would like to hear more about, I'd say, what's the difference? Because DTrace here seems like a higher level tool, especially since the rewrite is using BPF, while BPF trace is, writing BPF programs, as a base of the language. Thank you.
Well, I think you, I think in your question you kind of hit the nail on it. DTrace is kind of a more of a higher level tracing tool that, yes, uses BPF under the covers and, whether all other facilities where BPF trace is a little closer to just the BPF side. It's just two different tools, and I think it is hard to compare them. One aspect I think would be that, and I can't speak for anyone who would have termed BPF trace to be kind of DTrace 2.0. DTrace is a documented tool, so it kind of, unless you implement what is documented as being the behavior and the way it works and the way you can use it, it's kind of not really DTrace. Then it's kind of a DTrace-like tool. I would say that the goal for DTrace really is to stick to its original intentions, which is that it should be able to do very complex tracings, be able to be used for potentially also very long-term tracing at the same time. So I would expect that with BPF trace, you might be able to do similar things. Most users I've seen, and that's where I would say for myself, I put the biggest comparison is maybe a little lame, but the BPF trace, most of the examples I see are based on one-liners and not so much on more complex scripts, where I think the strength with DTrace lies primarily in its support to having more complex tracing scripts.
Other questions? Alexei?
It's more of a comment than a question. So you mentioned the issue with the K probes. So yeah, that was well understood. Same issue with U probes, and on the kernel side, thankfully, both were addressed in the most recent kernel. Now we have multi-K probe and multi-U probe. It's a different API, but now you can attach, I forgot what the test. Currently, we do a test with 60,000 of K probes all at once, and it takes like a split second to attach, detach. So this is fixed. And my question is how do you generate the code? Like, do you use some sort of like a mini compiler, mini optimizer when you're generating this code? Because you're saying these DTrace scripts can be big. So what approach do you use to like register allocate, for example? Because the way BPF trace did it is a front end similar to the DTrace, this language, awk-like language that feeds LLVM, generates LLVM IR, and rely on LLVM to generate all the BPF code. So what's the approach that DTrace took?
Thank you. And first of all, thank you for pointing out the work on K probes and U probes in the newest kernels. I'll definitely have a look at that. That sounds like a great progress. In terms of the code generation, so one of the underlying principles of DTrace has always been that it should be something that really can live on production systems and should have a very small amount of dependencies. I mean, ultimately, it's the main executable and a shared library. So we kind of have to stick to the notion that we can't really be a front end to something else like LLVM or whichever. So DTrace already had its own compiler to compile these scripts into what at that time was kind of diff code, was DTrace intermediary format code that was loaded into the kernel, into our own kernel modules. So we essentially have reworked that compiler to simply use BPF as its target. So we kind of redid the compiler, but since it already had a built-in one, that is what will be done. So it's a custom compiler that directly generates BPF code and then can link that dynamically generated code with code that has been pre-compiled from C into BPF using GCC. But the linking, again, is still done. So all the pre-compilation usually is done at build time for DTrace. And when you're actually doing the tracing, all work is done by DTrace itself.
Right. Nick?
There is no actual, you asked about optimization passes and so on for register allocation. We are using really simple-minded first come, first serve register allocation, which does sometimes lead to quite a lot of thrashing back and forth and spilling and so on. But I did a bit of an analysis of some of the resulting generated code, and there's not actually all that much because it's all straight line, throwing something, spilling something, and then pulling it back in again. It doesn't stress the verifier. It doesn't cause any kind of verifier state space explosion. You might gain a few, it might be a few dozen or 100 or so extra instructions, but when it's dealing with, when the limit is 1 million, that's not really a problem. It might be nice to optimize it more, but the more you optimize it, the more overhead there is for running quick DTrace scripts because you'd have to optimize it before you submitted it to the kernel. And people would like it to start fast as well as being able to run for hours. So there's a bit of a tension there. You could, in theory, I suppose, notice that it's been running for ages and recompile it, but how would you resubmit it without breaking the tracing? It seems like over-design even to me.
The thing is, there is definitely a goal, and it's been on my to-do list for too long, but that some work has been going into already in doing some form of optimization, and really the primary reason is the fact that the size of the programs, although not really being much of a strain, it makes room for other things. And some optimizations actually are really easy to be done. So that is definitely a work in progress. But the nice part is that right now, based on our testing and some performance testing, it does really quite well. So any optimizations at this point are kind of just added benefits. And on top of that, because we are working with a very custom compiler, we can be very careful with the way code is being generated. That we pretty much kind of pre-optimized a little bit the way certain things are being generated. So it's not a general purpose language that is being compiled. We do have a lot of control over what we're dealing with, and so therefore we can kind of pre-optimize the way the code is being generated to avoid a lot of those complications.
Other questions? All right, thank you.
Okay, thank you.